Applications of Differential Calculus, page 9. Number 13. Sam has sheets of metal which are 36 by 36 square. He wants to cut out identical squares which are x by x centimeters from the corners. He will then bend the sheets along dashed lines to form an open container. Show that the capacity of the container is given by this volume, x times 36 minus 2x squared. And then what size square should be cut out to produce the container of greatest capacity? Okay, so it's 36 by 36 total, and we're cutting out these squares that are x by x, and they're saying, hey, after you fold up the edges, and it looks kind of like this, tell me what the volume is. So the volume would be something like this dimension times this dimension times this dimension, and since it's kind of a square, this is equal to that, okay? And then this is the height. So the height is actually just x, right? So the heights are just going to be x because you're cutting out boxes. Each box is x by x, right? All right. And then what about the length? The length would be, you're cutting off an x by x box from each corner. So how long is this length here? It's going to be 36 minus x, right? Which is 36 minus 2x. Okay. And so the L is 36 minus 2x. Both of the L's are. Now let's calculate the volume. The volume is going to be x, which is the height, times 36 minus 2x, which is one length, and then we're going to square it because both lengths are both 36 minus 2x. And oh, look at that, we got that. Okay? All right, B. What size of square should be cut out to produce the volume of greatest capacity? Okay, so basically we're going to take the derivative of v with respect to x, and then we're going to try to see if we can figure out where the stationary points are. So let's see. I don't know what the best way to do this is. I don't like the product rule if I can do the power rule. So let's multiply this out. So we have x times 36 squared minus 72 times, it'd be like 144x plus 4x squared. And I can multiply that out. I'll have 36 squared is what? 36 times 36 is 1296. So we'll have 1296x minus 144x squared plus 4x cubed. And now I can take the derivative of that. Okay, so what I just did there was I just multiplied out v. So now v dashed would be 1296 minus 144 times 2 times x and 12x squared. So this is going to be 1296 minus 288x plus 12x squared. And okay, so now we're figuring out when does this equal to 0. We can use let's use poly-SMLT. And we're going to put in 12 for A2 because it's multiplied times x squared, and we'll put negative 288 in for A1, and then we're going to put 1296 for A0, and the two numbers, the roots are 18 and 6. Okay, so those are the two possibilities. Those are the stationary points. Now, which one of those is going to be the maximum? Which one is going to be minimum? We would have to maybe take the second derivative to find out. So the second derivative is going to be negative 288 plus 24x. And now we're going to do sign diagrams for both. So the sign diagram for v dash is going to be like this and like that because it's a open up parabola. And then for the dash dash, it's going to be something like, let's see, the critical point is going to be 288 divided by 24, which is 12. And a big positive number would make this positive, and a big negative number would make it negative. So let's see. Now we're looking for, this would be concave up, and this would be concave down. So that means 6 is going to be a maximum, and then 18 is going to be a minimum. So, oh, look at that. If actually 18, can you see what would happen if the little square was 18 wide? It would be like this big. So it's like you would just have a volume of 0, and that's why it's minimum. Okay? So, yeah, definitely the 6. The 6. So what size square should be cut out? It should be the 6 by 6 squares. If I would have really thought about that, I could have figured that out. I didn't need to take the second derivative. All right, 13. 15. A small population of wasps is observed. After T weeks, the population is modeled by this function here, where T is between 0 and 25. Find when the wasp population is growing the fastest. Okay, so we're going to take the first derivative to see if we can find when the population is growing the fastest. We're going to get, wow, that's going to be, we're going to have to use like the quotient rule, I think. So let's say that the top part is u and the bottom part is v. And so the quotient rule says u dash v minus u v dash divided by v squared. And so let's find u dash. U dash is 0 because u is just 50,000. And then v dash is equal to 1,000 times negative 0.5 e to the negative 0.5 t. Okay. So the u dash is 0, so that term becomes 0. And then we'll have minus u, which is 50,000, times v dashed, which is 1,000 times negative 0.5. Negative 0.5 times 1,000 would be negative 500, right? So we'll just go ahead and write that. And then e to the minus 0.5t. And then in the denominator, we're going to have v squared, so which is going to be a big mess. Ugh. Okay. So that is our derivative function. And we want to see when the wasp population is growing the fastest. So we need to see where the stationary points are for this big mess. So negative 50,000 times negative 500 is going to be positive something. Positive 25, 0, 0, 0, 0, 0, 0. 25 million to be exact. Okay, times e to the negative 0.5 t divided by 1 plus 1,000 e to the negative 0.5 t quantity squared. Okay, so this is the rate at which the wasp population grows. Now let's graph this and see when that quantity is maximum. We'll put y equals, and then we're going to program that in here. So we're going to put 25 million times e to the negative 0.5 t, e to the negative 0.5 x, because they don't have t, right? And then divided by 1 plus 1,000 e to the negative 0.5 x, close parentheses, squared. Okay, and then we're going to graph it. Ooh, weird. Let's do zoom fit. Okay, and so we want to know when this function is maximum. It's maximum right there. How do we find it? With second calc maximum. And left bound, we're going to go a little bit to the left of that hump, hit enter. We're going to go a little bit to the right of that hump, we'll hit enter. And the answer is 13.8. So the T is going to be 13.8 weeks. And I think we're done. Okay. 17. A right-angled triangular pen is made from 24 meters of fencing, all used for sides AB and BC of this triangle. So this is going to be the fence right there. Side AC is an existing brick wall. If AB equals X, find D of X in terms of X. And what is D of X? Oh, it's this. Find the length of the hypotenuse in terms of X. Alright. Oh, and by the way, that's a right angle. That's important. Okay. So, if AB is X, what's BC? So BC, let's say, is Y. How can we relate X and Y? Well, X plus Y happens to be 24, because that's how much fencing they have, right? So Y is actually 24 minus X. So I'm going to erase this Y, and I'm going to put 24 minus X. Okay. And then how do we figure out D from X and 24 minus X? Well, since we know that they form a right angle, we can use Pythagorean Theorem. So we can have X squared plus 24 minus X squared equals D squared. So D is equal to the square root of X squared plus 24 minus X squared, and we can multiply this out. 24 squared minus 48X plus X squared. Okay, and then we're going to put some of these together. So we'll have 2X squared minus 48X, 24 squared, which is 24 times 24, which is equal to 576. So that is part A, which is said to find an expression for capital D in terms of X. We did that. Now it says to find the derivative of the capital D squared function. When I first looked at this, I thought they were asking for the second derivative, but there's no squared down here, so it's not the second derivative. What they're asking for is the derivative of this squared. And we'll see why they're asking for that in a second. So this squared is just going to be simply 2x squared minus 48x plus 576. Okay? And what they're asking for is, hey, take the derivative of this, and you're going to get 4x minus 48, right? And then draw a sign diagram. So the sign diagram is going to be, like the x here is going to be something like 12. Let's find out exactly what it is. 4x equals 48, so x is equal to 12. And then if you put a big positive number in, you're going to get a big positive number. If you put a big negative number in, you're going to get a big negative number. So that's the sign diagram. That's what they asked for here. And then it says find the smallest possible value of D and the design of the pen in this case. So the first derivative of D, and the reason why they told us to find D squared instead of D, and I erased it, but I tried to find the first derivative of just D, and it's really messy. But if you think about it, if you want to maximize or minimize capital D, then if you maximize or minimize capital D squared, it's almost the same thing, right? So basically what they're saying is, well, since D squared is a much nicer thing to take the derivative of, because it doesn't have a square root, go ahead and maximize that, and then you've also maximized D. It's very clever, isn't it? So we know that the sign diagram for D squared dash is this. So it looks like 12 is going to be the minimum value, right? Because it's going to look like this, right? Negatives and then positive. Okay. So the value x equal 12 minimizes the value of capital D. Okay, and then we're just going to find the value of capital D. It's going to be equal to the square root of 2 times 12 squared minus 48 times 12 plus 576. And then that's just going to be equal to 288 minus, 48 minus 12. 48 times 12, not minus 12. 576 plus 576. Oh, how quaint. Okay. So square root of 288. 288 square root is 16.9. 16.9, actually it's 16.97, so actually 70.0. Okay, so the D value when x equals 12 is going to be 17.0. Okay, and that's what they're asking for. They said, what's the smallest possible value of D? In the design of pen in this case, so it's going to be 12 here, it's going to be 12 here, and it's going to be 17 there.